All right, we're finishing up Chapter 11 on probability, and we're going to look at expected value. So expected value is a weighted average. So we find expected value by using the following steps. It's a three-step process. So first we're going to create a probability distribution. And so this is a table that we're going to create. It's similar to this table right here. So X will always equal the phrase that follows the word expected within the problem. 2, once you create your table, you're going to multiply each X by its corresponding probability. And then 3, you're going to add these values together and you have figured out the expected value. Now the thing to know about this section is expected value is not a probability. So our answers can be outside of what we said probability answers had to be. So we said for probability we couldn't have an answer that was outside of a range of between 0 and 1. Expected value is using probability, so our answers could be negative, our answers could be greater than 1. All right? So first we're just going to practice completing a probability distribution table. So if X is a certain color, then some of the probabilities have already been given to you. Now, to check a probability distribution table, the probabilities across the entire table need to add to 1. So it would be easy to figure out if 1 was missing because we have 3 of them already. So we can see that this is 12, 13, 14, 15 19ths. So this has to be 4 19ths so that all the probabilities will add to 1. So let's get into some examples. So suppose that we wish to find the expected number of boys for a 3-child family. Complete the following probability distribution assuming that girls and boys are equally likely. So out of 3 children, you could have no boys, 1 boy, 2 boys, or 3 boys. And they're telling us some of the probabilities. So they're saying that the chance of having no boys is 1/8, and the chance of having 1 boy is 3/8. Well, we have to finish filling in the table. No boys is the same probability as all boys, so this is also 1/8. So now we can see out of all of these probabilities we've used up 3, 4, 5. So to have this all add to 1, this also needs to be 3/8. So all they're doing now in this column is they're taking a product. They're multiplying each X by its corresponding probability. So 0 times 1/8 is 0. 1 times 3/8 is 3/8. 2 times 3/8 is 6/8. And 3 times 1/8 is 3/8. Now it says the expected number of boys in a 3-child family. So remember the process. Complete the table, multiply each X by its corresponding probability, and then add those numbers together. So you're going to take 0 plus 3/8 plus 6/8 plus 3/8. So you get 12/8 or 3/2. Sometimes the answer that you get doesn't completely fall back to an option in the table, but 3/2 is 1.5, so we could expect that the expected number of boys would range somewhere between 1 and 2 because that's where the highest probabilities are. But your exact answer for this question is 3/2. So let's try another one, right? So the probability distribution table has already been given to us, and it's calculating the likelihood on how many absences a student would have in a math class. And they want us to find the expected number of absences. So since the table is complete, all we have to do is take each x times its corresponding probability and add those numbers together. So our expected value would be 0 times 0.12 plus 1 times 0.32 plus 2 times 0.35 plus 3 times 0.14 plus 4 times 0.07. So then we grab out our calculator and we get 1.72 days is the expected number of absences. Now we're going to get into problems now that require us to build our own tables. So we're going to play a game consisting of rolling a single fair die. And this is what happens. If we roll a 1, we get $8. If we roll a 2, we get 5. If we roll a 3, we get 1. And if we see any other number, we get no money at all. So we want to find the expected winnings for this game. So we got to build our table first. So x is always what follows the word expected. So we're looking for what is our average winnings. So we're going to build a table here. So the amount that we could win has been told to us. We could win $8. We could win $5. We could win $1. Or we could actually win nothing because it says, and no payoff otherwise. Well, how do you win $8? You have to roll a 1. So the probability of winning $8 is 1/6, because remember our sample space for rolling a die is 1 through 6. We win $5 by rolling a 2, so that would be 1/6. We win $1 by seeing a 3, which would be 1/6. And then this is 3/6 because we need it to add all to 1. So now our expected winnings are found by taking each x times its corresponding probability. This one is 0. 0 times anything is 0, so we don't have to really include this one in our work because it's not going to add or take away anything. So I'm going to write 8 times 1/6 plus 5 times 1/6 plus 1 times 1/6. You could add in plus 0 times 3/6, but it won't add anything. So work done is 14/6, which is 7/3, which is $2.33 is our expected winnings. All right, let's play a different game. So a certain game involves tossing 3 fair coins, and this is how it pays out. 10 cents for 3 heads, 5 cents for 2 heads, 3 cents for 1 head. What are the net winnings for this game if it costs 5 cents to play? And then, is 5 cents a fair price to pay to play this game? Well, the first thing that might make this problem easier is to think about what is our sample space. What are the exact ways this can play out if I toss 3 coins? Well, I could get heads, heads, heads. I could get heads, tails, heads. I could get tails, heads, heads. I could get heads, heads, tails. So that's 3 heads, 2 heads. I could also get heads, tails, 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 heads, tails, or tails, tails, heads, or I could finish with all 3 tails. So we see that if I am tossing 3 fair coins, these are the 8 total options I have in my sample space. Now we need to find our probability table. So x is always equal to what follows the word expected. So what are the net winnings? And then we have our probability side of our table. So what is one amount we could win? Well, we could win 10 cents, but we have to talk about this net winnings idea. Net winnings takes into account what it cost you to play. So when you find net winnings, you have to take your total winnings minus how much you paid up front. So we're going to say 0.10 minus 0.05 could win us 5 cents because we paid 5 cents to play. Another one is 5 cents, so 0.05 minus the 5 cents we paid, so we actually break even. We don't win or lose. We just got back what we paid. We could win 3 cents, but we paid 5 cents, so we've actually lost 2 cents. That's a negative number. And then the other option is we don't win anything at all, so we've lost our entire nickel that we had to pay. So now let's figure out the probabilities for each of these. Well, we won a nickel by seeing 3 heads. That's in my table 1 time out of 8, so 1/8. We won 5 cents by seeing 2 heads. So here's 2 heads, here's 2 heads, here's 2 heads. So that's 3/8. 3 cents was won by seeing 1 head, so that's these, 1, 2, 3, so 3/8. And then if we see here, the only time we ever won money is if we saw some number of heads. So if we see all tails, we win nothing. So this is 1/8. Now we want to find our answer by multiplying each x by its corresponding probability. So we're going to take 0.05 times 1/8. The 0 one we don't have to add in. 0 times anything doesn't add or subtract from our answer. So we're going to do minus 0.02 times 3/8 minus 0.05 times 1/8. Now I don't even have to get out a calculator to tell me that this one and this one are going to cancel. So this right here is the only calculator work I really need to do. So when I multiply that together, I get negative 0.0075. So my expected net winnings are negative. So answering that second question, is 5 cents a fair price to play? Actually, no. 5 cents is not fair because we end up losing money. A fair price would be where the expected net winnings is actually equal to 0, meaning we don't have any better chance of winning or losing money. All right, 5. So we have a college foundation raises funds by selling raffle tickets for a new car worth $36,000. 600 tickets are sold for $120 each. Determine the expected net winnings of a person buying 1 ticket. So X is net winnings. And then we're going to figure out our probability. Well, you buy a ticket in the hopes to win a $36,000 car. But remember, net winnings takes into account what you paid to play. So we bought a $120 ticket. So that would actually mean our net winnings are $35,880. The other option is we don't win. Well, we paid $120, so we're out $120. Well, how do we win the car? We win the car by our raffle ticket being pulled. Well, how many did we buy? We bought 1 ticket out of 600. So our probability of winning is 1 out of 600. Our ways of losing are 599 other tickets out of 600. Okay, so let's find our expected net winnings. So we're going to take 35,880 times 1 over 600 minus 120 times 599 over 600. If you compute this with your calculator, you get a dollar amount of negative 60, which tells you that you are not likely to win if you buy 1 ticket. So this is all of the work for Part A. Part B says, what's the total profit for the foundation assuming they had to purchase the car? Well, that's nothing to do with probability. That's just some common arithmetic skills, right? They sold 600 tickets at $120 each, which is $72,000, but they had to purchase the car, which is $36,000. So $36,000 is what that club could expect to gain if they sold all the tickets and they had to purchase the car. Now C says, what's the total profit if the car was donated? Well, you only do the first part. You do 600 times 120 and you get $72,000. And you stop because the car was donated. All right, 6. In a certain California city, we're going to talk about what are the projections for next year about the number of electronics jobs. So we want our X to represent the expected change in the number of electronics jobs. Now this one's pretty straightforward because they give us the probabilities right in the word problem. So there's a 20% chance that jobs will increase by 1,200. So jobs could go up by 1,200, and that's 0.20. There's a 50% chance they'll increase by 500. So 500 is 0.50. And then there is a 30% chance they'll decrease. So we need to use a negative to show a decline, and that is 0.30. Now, to check your table, these need to add to 1, and we see that they do. So our answer is just found by multiplying each X with its probability and adding those values together. So I grab out my calculator, you would do the same, and you get 250. A positive number here suggests that there's more likely going to be an increase in electronics jobs over a decrease. Problem 7 is just 3 separate tables that need to be computed. So Nick has got an opportunity to invest $5,000, and he's wondering which company he should go with. So he's going to find the expected profit or loss for each of these tables. So here's the first table, here's the second table, and here's the third. Right? So A, B, C, the table's already done for you, so all you have to do to find the profit or the loss is multiply each X by its probability. So you're going to take negative 400 times 0.2 plus 800 times 0.5 plus 1500 times 0.3. And you're going to see if Nick went with ABC, what would be the likely outcome. So we get $770. So now we're going to do our ST. Same thing. So we're going to do 500 times 0.8, and we're going to do 1,000 times 0.2. So remember, when you're finding expected value, you multiply each X by its corresponding probability. So this is 600. So we have one more. We have X, Y, Z. So 0 times 0.4 doesn't add or subtract anything from our table, so we don't need to put it in. So 700 times 0.3 plus 1,200 times 0.1 plus 2,000 times 0.2. And we get 730. So the company that Nick should go with would be that company that has the greatest expected profit. Well, that would be ABC, because their expected profit, if he would go with ABC, is 770. So even though there's a potential for loss, there's a greater possibility of a bigger gain than the other two companies can offer him. All right. So now we're going to go back to raffle tickets again. So 15,000 raffle tickets are sold. A prize of 5,000, a prize of 2 prizes of 1,000, 3 third prizes of 250, right? So we want to know what's our expected gross winnings. Now the difference between gross winnings and net winnings is gross winnings is just straight up what you win, paying no attention to how much it cost you to play. So the biggest amount we could win is 5,000. We could win 1,000. We could win 250. We could also walk away with nothing. Okay, so how do we win 5,000? Well, there's one prize. So there's 1 out of 15,000 tickets, right? There are 2 out of 15,000 that could be 1,000, and then there are 3 out of 15,000 that could be a third place. This is the fraction that would add all of this to 1, but remember you're multiplying by 0, so it's not needed in the table. So we're going to take 5,000 times 1 over 15,000 plus 1,000 times 2 over 15,000 plus 250 over 3 over 15,000. And we end up with an answer of 52 cents, which tells us we're not likely to win any of these 3 amounts. Couple more in this section. So we have an amusement park, and they conducted a survey and found on a typical day how many families are entering the park with a certain number of children, right? So there's 10,000 families that they looked at, and they were looking at, well, how many kids did they bring with them? So we need a table. So X is the number of children that the family brought. And X is the probability of that size family. Well, they run through 1 child up to no children. So 1, 2, 3, 4, 5, 6, or none. Right? Well, how many families brought 1 child? 10, 20. So this is 10, 20 out of 10,000. 2, 3370. So this is 3370 out of 10,000. 3, 3510 out of 10,000. 4 would be 1340 out of 10,000. 5 would be 510 out of 10,000. 6 would be 80 out of 10,000, and then this is the fraction that would add all this to 1, but since you're multiplying it by 0, it's not necessary. Now how do you find the answer? You take each x times its corresponding fraction. So you're going to take 1 times this fraction, 2 times that fraction, and you're going to add all this up. I'm going to let you do that for yourself. Your answer is 2.7. Which makes sense because that's where the biggest probabilities lie. Last one. 4 cards are numbered 1 through 4. 2 of these cards are chosen randomly without replacement. That means you're pulling 2 distinct cards. You cannot pull the same card twice. And the numbers are then added. Find the expected value of this sum. Well, the first thing we have to do is we have to know, well, what is the possible answers to the game? What could we see if we were playing this game? So we need a sample space. The greatest way I know to make a sample space here is to go back to chapter 10 and use a product table. So I'm going to write across the top and down the side that I have cards numbered 1 through 4, and I am pulling 2 cards without replacement. And I am adding them. I cannot pull 1 followed by 1 because without replacement means they would have to be different. But I could pull a 2 and a 1 and add to 3, add to 4, add to 5, add to 3, add to 5, add to 6, add to 4, add to 5, add to 7, add to 5, add to 6, add to 7. Right? So I see my sample space. Now I want to know, well, what are my possible sums? Well, I look in my sample space and I see a 3, 4, 5, 6, 7. So now my table also tells me the likelihood this would occur. How many times do I see 3 in my table? Twice out of how many over here? 12. So I get 2 twelfths. 4 is also 2 twelfths. 5 is actually 4 twelfths because it's in there 4 times. 6 and 7 are also 2 twelfths. So to find my answer, I'm going to multiply each of the x's by its corresponding probability. When I do that, my answer will be 5, which makes sense because it's in the table the most number of times.